Hi, everybody. My name is Daryl Salas, a sales director in Neo4j, joined by...
Hi, this is Amay Mahajan. I'm a sales engineer and data scientist at Neo4j.
Okay, and we're here to present on real-time payment fraud prevention. Next slide, please. So fraud is a big problem. Payment fraud is a big problem. Any company that does transactions using any of the real-time payment rails, including credit card systems, has to be very concerned about the fraud problem, because it ends up costing tens of millions of dollars a year for large enterprises. And you have to make decisions in real time. So you don't have a lot of time to think about every single transaction that comes in, especially when you're processing large volumes of transactions in real time. Not only is there the cost of the fraud, the direct cost of the fraud that's involved, but also it can impact the reputation of a company. So if a large company has a lot of subscribers, tens of millions of subscribers, and they experience, anybody becomes a victim of a fraud, it hurts the reputation of that company, and that results in added cost as well. And this is a very difficult problem to solve. The problem being, how do we get better at preventing fraud in real time, so that we can reduce these costs and maintain our reputation. The reason it's a difficult problem to solve is because of the large volumes of data and the fact that you have to make these real-time decisions. Traditional systems, they either either update their scores in batches daily, and then they don't have great predictions, or they update their scores more in real time, but then they can't handle large volumes of data. What we're going to present is a way of doing both, where you can have a graph ML driven fraud prevention solution that has very accurate predictions, a lot more accurate than a company is getting today, continuously learns, is very agile, and can do all of this at extreme scale. Next slide. And so this is the architecture that Amay is going to talk about. So we have a single cluster in the architecture, and we have primary servers and secondary servers in the cluster. And on the secondary servers, we have that's the analytic part of the cluster. So we're doing every 10 minutes, we're running graph algorithms at scale, weakly connected components, Pagerank, other Centrality algorithms, and we're running them every 10 minutes or so, and updating scores. And in the meantime, in between those runs, we're also doing unsupervised machine learning using pattern matching on the unscored nodes in the graph. So you could have billions of nodes in the graph and billions of relationships. Typically, you see three times the number of relationships per node. And to be able to do all of this at scale, you really have to have all the data in the same system that does both the operational pattern matching and ingestion or transactional processing. The transactions in this case are prospective credit card transactions that you have, let's say, 100 to 200 milliseconds to make a decision on whether you're going to accept or deny these transactions. And it all has to be real time, and you have to detect suspicious, I call it rings in this case, or suspicious patterns. And so the entities, and the reason I call it rings is because there are patterns across different entities. So I mentioned transactions, you might have accounts, you might have devices, IP addresses, payment instruments. And so you're looking for patterns across all of these that look suspicious. These are things that you can't detect unless you have a graph database. And the features that you're running from the analytical part of the cluster, as I mentioned, we're refreshing those every 10 minutes and writing back to the leader node. In this case, we put the top blue node as the leader node in the cluster, but any of the blue nodes can potentially accept writes, and those are part of the operational cluster, the operational part of the cluster. Next slide. Okay, that's you, Ame.
Yep. Thanks, Daryl, for that overview. So let me go over the specific use case, in this case, like real-time fraud detection for accounts. I wanted to lay out a couple of objectives, not just in terms of technical objectives, but also what are the business drivers and why this becomes a graph problem. I mean, fraud is something which will involve a lot of relationships and network analysis. So inherently, foundationally, it becomes a fraud problem. This specific use case is about real-time detection of, like Daryl said, suspicious transactions happening that might be using one or more entities around your account. So consider this account as like a gaming console account that you might have, and you will be having your emails. You will be doing transactions like buying games, buying skins for players, all sorts of those kind of transactions, building your profile on that gaming platform. um, and those transactions will take in your email address, IP addresses, the device or the actual console that you're playing on or working on, your credit card or payment account. And all of this information we used in this use case, and we created a network like you see the graph data model on the side here. And what we want to do is, given the historic data of transactions around your account, we want to calculate risk scores for these entities that I just mentioned, build these new additional graph features, and combine it with your non-graph features that you already have in terms of a non-graph model, and test out the results of how a graph can actually boost that performance and overall result. The business drivers: every declined payment or transaction that happens, or a fraudulent activity that happens, like Daryl mentioned, it costs about millions, or even like higher range of millions for these companies. So just in penalties that they might have to pay to the bank. And every percentage improvement that we can get out in the existing models can actually end up saving millions of dollars. Those are the key business and technical objectives of this, were the business objectives and technical objectives of this use case. Some of the key questions that we started off was identifying some suspicious patterns, like is there a particular pattern that people are following, like a small big, basically doing a bunch of transactions in a particular order, trying out a first few. If they go in, then do a bigger transaction and cash out. That's one of the patterns. That's something called as bot attacks, where you have a bunch of email addresses that you either create and connect to a specific account, or use an identified IP or an email address and bombard it with, say, around 10,000 transactions per second, and use those. If even like a percentage of those transactions go in, the fraudsters are going to get money, and then the same thing happens. The customer reaches back to the company, and then the company has to pay penalties. So those were some of the key questions. And the third one is actually tied to the graph data science piece, where we are trying to build features, and we want to use the shared entities or the cross domain knowledge across. If there are people sharing one or more entities, creating graph features out of it, and then can we have graph based scores based on what your topology or your network looks like, and then using that as a feature. And in identifying fraud beforehand, basically a live transaction comes in, gets connected to one of these entities in the graph. We already have a graph based score. We say that, yep, it's risky, go for it, there's a threshold, block the transaction. So we are doing more of a proactive approach to stop fraud in real time, rather than a reactive approach. So why graphs? This slide touches upon why graphs, and I wanted to focus specifically on that highlighted box there. The current strategy, generally there is like a five-way approach that a fraud strategy or fraud detection strategy has. But the most important part to look at here is the cross domain analysis and linked network analysis. We want to track user behavior, not just limited to his or her own set of transactions and behaviors. We want to track that behavior across across different users and across different domains. Is a user sharing some kind of an email address with some other user who is risky, or is the user trying to access a device which that user should not access? So that kind of cross domain analysis and the behavioral patterns that the users or fraudsters specifically simulate or generate is very important to capture in fraud, because we need to there are a lot of quote unquote normal behaviors in a fraud use case, and identifying that gray area where a user might seem to be behaving normally because they are using clean devices or clean entities but are in fact very risky, is something that the graph gives you. The last one is linked network analysis, which is again an important piece, because that actually is using your topography to calculate all these GDS based or graph data science based features. And the traditional approaches don't have that kind of visibility, and those don't give you that kind of an insight when the graph becomes huge in the scale that we are talking about. The graph approach will do it for you. Um, this is the architecture for the use case. And if you see from the left, what users are doing is they're pumping in continuous transactions that are happening, and we're using streaming data that the data that's in that streaming data feed is read off of, and the orchestration code layer pushes it in the Neo4j database. What happens in Neo4j database is, I'm going to dive into that, but it's going to be like the GDS workflow, which is the batch-wise GDS workflow, the left box there on the bottom, which effectively is running your bunch of algorithms parallelly at scale every 10 minutes and recalculating and recomputing these risk scores for accounts, email addresses, IPs, devices, credit cards, etc. So every time, every 10 minutes, when I have a real live risk score for any entity that I have in the graph, which is used when any kind of new transaction comes in. Why 10 minutes? Because every 10 minutes, we expect the traffic, it's about 100 to 200 transactions per second. So the graph keeps evolving. There are new kind of patterns that keep building, and we want to keep calculating these risk scores for the evolving patterns and be as real time as possible. Now, what happens between those 10 minutes when my GDS workflow is running and when those 10 minutes is that real time scoring workflow, where we identify, are there any new kind of patterns growing. So let me dive into that specifically. um, like I said, every entity is going to have a risk based score associated with it, but there are fraudulent patterns where completely new set of entities are used, and within a matter of minutes those entities are used where we don't have any kind of background about those entities, meaning we don't have any kind of scores for those entities, are used to create and perform fraudulent transactions. The second real-time workflow scoring workflow box that you see is another set of basically a workflow that we run, that we developed, which will identify these newly growing patterns and start tagging those as risky elements in the graph. So that is the real-time piece where it will become like, oh, okay, this is actually something that needs to be flagged right off the bat, because that's something which is growing and I don't have any knowledge. My data science workflows don't have any knowledge about that. Once you hit the 10-minute mark, those new patterns will again go back in the graph and they'll be used, and they'll have a specific score for them. Just diving into the results part, this is what we tested out on our end. We tested out on a bunch of data points that we got. And what we saw in terms of model enhancement is almost a 40% uplift. In recall metric, we observed almost more than 20% uplift. And most important part was, given a set of 325 or 400 features, the top 25 features had almost one third of those were Neo4j features. So that's what is the real kick in terms of from a machine learning standpoint, because just with 25 features, almost 10 or 11 of those start showing up as your top most 25 predictive features. And that's really an important aspect to look at in terms of developing your project, your fraud project, from like phase one, phase two, phase three, because you start with a list of graph features, you keep on building it. And we try to translate it into by reading online and learning how the fraud industry actually, how the industry actually works. And we expect of an uplift in terms of revenue of almost 10 to 13, 10 to 12 million, or even a higher range per year once we implement this kind of a use case. One of the other important things that you also see is the right side here, which the graph or the network gives you, which is the suspicious patterns which fly under the radar. So what you see in blue here, you can consider those as a bunch of transactions. The purple nodes are accounts which are connected to each other because they share some kind of an entity. They might share an email, they might share something. In this case, they're sharing this yellow email. So all of these accounts are actually trying to access one email, which in itself is a very suspicious pattern, which the graph identifies. But the graph also identifies these red highlighted arrows that I just did. By themselves, these orange devices and this green credit card is clean because they are not shared across different accounts, but they are in the same community as this risky email. So if you see, there are one or two hops out with that risky email, and that's what makes the graph problem. That's what makes it a graph problem, and gives a even better insight into what's happening. I'll quickly dive into what these actual workflows are and what we have built upon. So this flowchart actually gives you an example of the different kinds of workflows and sub workflows at a high level or in a detailed level that are happening on the fraud on your transactional data. The first thing that we do is we derive these different kinds of relationships that you see. What you saw is accounts. They might be sharing these entities from the data model. What you then start doing is create these account to account relationships and get your account level homogeneous graph. Once you have that graph, you start feeding that graph into the GDS workflow, the graph data science workflow, which, as I said, runs parallelly. So a bunch of these things are running parallelly, where you first calculate page rank. We ran weighted page rank so that we know exactly based on how many emails or devices or entities that person is sharing. We feed the topology, we calculate the page rank risk score. Higher the page rank risk score means that person has a real high influence in the overall network, and that means that person is actually sharing a lot of entities which they should not be sharing, and that's what makes them risky. Second approach, or the along with that, we are running degree centrality, which gives us a straight away a straight filter as to, okay, show me all accounts sharing more than 3 email addresses, 4 email addresses. These risky entities are actually important for us to calculate community detection, because when we run community detection, we run it on these smaller subgraphs of risky entities. The riskiness is defined by the GDS algorithms like Centrality or PageRank, and then we feed those risky subgraphs into a community detection algorithm to find out what are the impacts in my overall network. Are there any clean people, like I showed a screenshot of, who are flying under the radar, but are in the same community as those risky entities? I need to start calculating risk scores for them and start blocking transactions if there are any. And the last part of the GDS workflow is exporting these features out and running your auto ML model or any kind of model that you already have in place. So all of this workflow, if you go into the details of how you run these GDS workflows, there are multiple steps of projecting a graph, running the actual algorithm, writing it back, and then storing back the results and pushing it in the graph. And all of this parallel GDS workflow that I'm telling you, we run that every 10 minutes to compute and calculate all these scores that are coming in. That's the first box of parallel GDS workflows and how it feeds into the overall scoring mechanism. The second part is the real-time part, where between those 10 minutes, we now need to start identifying risky entities or risky clusters of entities that have started building upon and people are doing transactions with. They can be potentially fraud because they'll just basically choose a fresh set of email address, IP, device, and it can also be a clean account. So it's like, let's say I'm a new person and I'll sign up for my account. That's going to start showing up as that new pattern. But if a fraudster is using any of these entities, they will be using some of these key entities to create to start hitting multiple accounts using those fresh set. So that's what we are trying to track within those 10 minutes and to see if there is a cluster that's starting to develop. So the first thing that we do is this a completely fresh set of nodes? Meaning, because we already have a GDS based score for the existing entities, we first check that if your these entities that have come in, are they completely fresh? Do they have any GDS scores? If they do, you already have a mechanism to calculate the threshold, the risk score, and block it or not. If not, then you go to step two, where you start going in the network that is building real time, and you start looking at, okay, this is the community size that went from 10 nodes, 10 devices to 25 devices. Nothing is shared, so it's okay, it might be clean. But then it starts growing in the last minute or so. You see that there are different transactions getting connected to multiple new devices, and that's what starts forming a pattern like this, where on the left side what you see is a transaction one, where everything is clean, a new set of accounts, IP, payment accounts, email addresses are there, and a device is there as well. But as soon as you come to transaction number 5, which is, let's say, like say in the last 100 milliseconds or 10 milliseconds or something, you start seeing that a second account was created with the same device ID, separates IP and credit card information, but the same thing was done. Cut to transaction 23, the same graph, the same pattern got built because there's an email now that is getting shared between account 2 and a new account 3, which has its own entities. So now if you see holistically at this whole new cluster, this is the real time part where we actually are identifying this cluster, and we are saying, hey, look at this device. It's actually sharing an account uh, with something which is sharing an email with an account 3. So if you start from account 3, you can hop back in the graph real time and calculate these risks based scores based on just the community or the relationships that got built uh, during these transactions were happening. And I want to stress upon the point where this is happening before even your GDS workflow is running. This is happening real time, because the next time the GDS workflow that I showed will run, these are going to get higher scores. But you're going to get an insight into these higher scores of and blocking these entities at real time, because you can see in the graph and query the graph in sub-second time to actually start looking at the results. And that's what's happening in terms of these real-time workflows. I just wanted to point out one more slide here. Yeah, so in this slide itself, if you see, we can start calculating these risky devices and email counts based on an anchor point. And once we have these features written out in the graph real time, you can actually then feed it to these additional features and build more features or more weighted features around these. If you know that people are flying under the radar or new people are starting to emerge in your cluster, you can start assigning them higher weights. We tested out both of these workflows. I'll go back to the architecture here. Both of these workflows, this whole architecture with around 600 million, 500 plus million nodes, 2 billion relationships, and the real-time volume of 100 to 200 transactions per second. So multiple aspects in terms of SLAs come into picture here, because what we are trying to do is we are trying to do live scoring as well as run these algorithms. So the SLA is about 50 milliseconds for just the graph piece, because once I hit a transaction, once a fraudster says, okay, do this transaction, you as a company have 100 milliseconds to decide if it was a fraudulent transaction or not. The SLA was 50 milliseconds were assigned to the Neo4j side of it, where we are like, okay, let Neo4j do its job in 50 seconds. The performance that we got even at this scale was less than 2 milliseconds. where we could read and do live scoring at this scale through the different algorithm runs that have happened, retrieve the scores, and say that, oh, this is the threshold. What do you want to do with these transactions? All of that retrieval part was about 2 milliseconds when you run it on Neo4j. Daryl touched upon it. The architecture that we used is three primary machines and two GDS machines here, the analytical clusters, the 3+2 hybrid. And the two analytical clusters will make sure that it's high variability for one, but it's also going to run multiple of these workflows parallelly. So the workflows get split across your GDS machines. And so that's horizontal scaling. And you can also do a vertical scaling by running these algorithms concurrently. And that's how we achieved the different SLAs that we want to meet in terms of algorithm workflows and the real-time workflows. I Thank you. I'm looking at questions, Daryl, if you want to add anything, but I can answer that question from Steve. Yeah, so there are a bunch of, we did experience a bunch of data quality issues, but the ingestion part, which is again another workflow in itself, we make sure that we are pre-processing these data sets that you're getting, and we're using bulk imports. So even if we ourselves experienced we had to reload the data a bunch of times because say some part of the data was wrong, but just using the bulk imports made sure it was really fast process. But yes, there are a bunch of issues in terms of having the getting the right quality of data in this.
Yeah, I think the data quality issue, it's not just a matter of data quality in the production system. When you load the data in, you want to have the right granularity of data. So initially, I think a little bit of upfront planning we had to do a little, because if you plan it wrong and you load like a half a terabyte of data, and then you notice that you don't have the right granularity, then you have to reload the data. So you want to make sure you do some upfront planning for that as well. But as far as the question whether these algorithms are going to work if you don't have like perfect data quality, they're it's still going to work, right, Ame?
Yeah,
it's not going to work perfectly, but it's
still going to work. It's going to still create the features. Yeah.
I mean, so it's a matter of data, garbage in, garbage out to some extent.
Yes, Simon, do we have any issues with deadlocks? Yes, we have to plan those workflows so that the real-time workflow and the GDS algorithms don't make sure they're accessing the same accounts. So that's the orchestration layer that we have to focus on to access to deal with the deadlock issues. But yes, that second part that you see here, streaming data to orchestration layer, all of that needs to be worked on in terms of what scale is coming in, how are you orchestrating that, just the code in terms of the orchestration layer code. If you're using some kind of a function there, how can we time those, and what kind of concurrencies you're using, all come into picture to address the deadlocks issue.
Yeah, so any transactional system, Neo4j is a transactional database. And the initial slide, we talked about how there's an operational part of the cluster and an analytical part of the cluster. Any operational database or transactional database has to be able to manage concurrent writes. And so managing those so that you don't have locks being held for too long. So it's more of a design and planning issue. There's some techniques, like you don't want to have really long transactions that hold locks for too long. There's some things like that.
Or having in your orchestration layer, if you have a long query, just a single query that makes sure that all nodes and relationships are going in at the same time, you might want to split it so that nodes go in first and the relationships next. Because if you have one big query in your orchestration layer, if you have one big query, it has a potential of locking the other nodes if one of them is getting stuck. So you have to make sure that the orchestration source code the part there is well planned and well implemented. How many features do you use in this case? 25 to 30 features based on IP, email, device, credit card, all the entities that you saw. But then, like, so let's say PageRank risk score, it will be for all entities. Community risk score will be for emails, devices, and say credit cards. So all in all, it's around 25 to 30 odd features that we in the first pass. You can always keep building on these features. Like I said, like if it's like a risky entity in people flying under the radar, basically that means how many hops am I out from a risky entity? That was not included in this exercise, but that's something that you can start including, that hey, I'm 3 hops out from a risky entity, or 1 hop out, or 2 hop out, so that can be an additional feature.
Yeah, and as far as recommendations, we do have that real-time component to our demo where we can stream in transactions and in real time predict suspicious entities associated with those transactions, which is essentially a recommendation of what's a suspicious entity. But for, let's say you had a product recommendation type of use case, like, would you be able to use the same data set, Ame, or?
Sorry, Mr.
Like, let's say you wanted to make recommendations to the subscribers. I don't know if that's what the question was, but if you wanted to extend this fraud use case to personalized real-time, personalized use case.
Right. We can, because if at the end of the day you have transaction data, so you know exactly what kind of products are being bought using those transactions. So the actual the product titles. So that from that we can basically say, okay, these people are interested in this kind of genre of say games or anything that they're buying, right? So because it's transaction level data, the workflow would still follow a similar route. Let me go here, because the first part of the derived relationships that you see here, that will be a bit different for recommendation use case. That will be basically based on user behaviors or product patterns or buying patterns that the user has. But yes, we can definitely use it, and then we can maybe use embeddings in this in product recommendations case to just know exactly how the different users are doing those kinds of transactions. So yes, it's possible.
So looks like we're at the end of our time slot. Want to thank everybody for joining us and taking the time to hear our presentation. If you need to reach us, you can email us at firstname.lastname@neo4j.com, Daryl.salas@neo4j.com, or Ame.mahajan@neo4j.com. Yeah, and I think people will be receiving the presentation as well. Thanks, everyone.